Um, Two things. One question that came up last week is the idea of power ratio or power factor. So just to address that a little more, since I have all this up here, you should understand that if you have an LC circuit, your inductor and your capacitor are going to run out of phase. So when your inductor has all its energy, the capacitor has no energy. The inductor gives up energy to the capacitor, which builds energy. The inductor loses its energy, then the capacitor gives it back. And so you have this oscillating circuit in much the same way that a pendulum goes from zero potential energy but a lot of kinetic energy at its equilibrium position. Then it swings out to equilibrium and comes to rest for an instant. Kinetic energy is gone, but it's got potential energy, which it then regains as it swings back. Keeps going back and forth. The equations are the same, except for the names of the constants. Okay? Many things are that way, which is another argument for deep learning. A mechanical system with a linear drag force and a linear restoring force behaves, the mathematics is exactly the same as it is for an LRC circuit. And there's a complete analogy. I just mentioned one of them, the potential energy, kinetic energy versus the energy stored in the inductor and the energy stored in the capacitor. Okay, as it relates to power, many systems of completely different types have exactly the same mathematics, or closely related mathematics. So if you understand one, you can understand the other, and you don't have to do all the mathematics. You don't have to relearn all the mathematics. You want to look for things like that. Okay, well, back to the power factor. Okay, we have this oscillating LC circuit. It's not losing any energy. Okay, there's no resistor in this circuit. Okay, so the circuit loses no energy, but it's still running current. Okay, and that current has to be supplied by the power company. That current runs through the power company's lines. Okay? Now, it doesn't affect your power bill. Well, actually it does, because the power company's probably going to figure out that you're way out of phase and charge you for that. They charge penalties for that sort of thing. But you're not dissipating any energy, so there are no kilowatt hours involved. You're not paying for that electricity unless they fine you for it. Or some other way, give you a fair charge for what you're doing to them, because the current that runs through their lines runs through the resistance of their lines, and their lines have resistance. Now, your circuits also will have a little bit of resistance. Okay, you're not going to get a circuit without resistance unless you're running superconductors. And with capacitors and inductors, well, I'm not sure exactly how that works out. I don't work with that stuff. You're not dissipating much energy, okay? Maybe you're not dissipating zero energy, you're not dissipating much, so you're not paying for much power. The power company has to supply the power to run the current through the resistance of its lines. And that's a significant amount of resistance, so that costs the power company. So you're using current without actually playing the game fairly, although you might be trying your best. Well, the power company comes after you and says, hey, look, your power factor is terrible, it's zero. Well, what's that mean? It means that you're running all your current through something that doesn't actually use any energy, or it uses almost minimal energy. And you're not getting charged for it, power company's paying for it. So they tell you, okay, put a capacitor in parallel with the circuit. I'm not going to talk about how that works, but it's not that hard to figure out. That changes the phase of your circuit, so it's in phase with the power company. And now things get a lot happier. Now, that's just an example, and a start for understanding the idea of power factor, how that works out in a practical engineering type situation. Another thing I mentioned, not unrelated to that, is we talked a fair amount about symmetry. You have all these symmetries. Toroidal, a toroid has a certain kind of symmetry. A cylinder has a certain kind of symmetry. A sphere has a certain kind of symmetry. Those symmetries come in when you're trying to apply Gauss's law or Ampere's law or whatever, or many of the laws of physics. Those cases that I mentioned are cases that you're familiar with. So I'll just mention, I just saw an article in some, not rigorously scientific publication about Emmy Noether, who did some work with. It was kind of centered around symmetry. Just a good name to look up, and in the context of the symmetries that we get when we apply Gauss's law or the divergence theorem or Ampere's law, which is an instance of, or very, very much related to Stokes' theorem. These things are, when applied in certain types of symmetry, give you really profound results, okay? So just within the context of the idea that symmetry is important, you might find it interesting to look up Emmy Noether.